Okay, in this video we are going to consider some 25 statements and say whether the statements are true or false. First question, first statement: if a random sample of size n is drawn from normal distribution with mean mu and variance sigma square equal to 1, then 1 by n summation xi square is the unbiased estimator of mu square plus 1. I am verifying it. I am taking the expectation of this expression. So I get 1 by n summation expectation of xi square. What is expectation of xi square? This is the formula. Variance of x is expectation of x square minus expectation of x the whole square. So expectation of x square is variance of x plus expectation of x the whole square. So variance of x is given as 1. Expectation of x is given as mu square. So it is 1 by n summation 1 plus mu square is 1 by n times of 1 plus mu square, because you don't have the running variable I here. N and n gets cancelled and you get this answer. So the unbiased estimator of this is this. The statement is correct, true. Next question, MLE of the parameter P of Bernoulli distribution is this. It is true. And MLE of the parameter P of binomial distribution is x by n. Yes, that is also true. If mu is known, MLE of sigma square is. If mu is known, MLE of sigma square is simply that value which is known to you can be substituted here. Right? You need not substitute by the MLE of mu, which is x bar. So this statement is false. When mu is known, MLE of sigma square is summation xi minus mu the whole square by n. When mu is unknown, what should you do? You should substitute mu by x bar. So this statement is also false. When mu is unknown, MLE of sigma square is summation xi minus x bar the whole square divided by n. This is the correct statement and this is false. Okay. Now, the next one. S square is equal to summation xi minus x bar the whole square by n is an unbiased estimator of sigma square. No, it is false. Right? Because if you compute the expectation of s square, you will get sigma square into 1 minus 1 by n. You will not get sigma square. Okay? You will get sigma square into 1 minus 1 by n. So s square is a biased estimator of sigma square. Remember this point. And s square is equal to summation xi minus x bar the whole square by n is an asymptotically unbiased estimator of sigma square. Now let us check. Put n is equal to infinity. When n goes to infinity, 1 by infinity becomes 0 and you get sigma square. Yes. So when n tends to infinity, this s square is an unbiased estimator of sigma square. So the statement is true. S square is asymptotically unbiased. Ordinarily it is not unbiased, but it is asymptotically unbiased. On the condition that n tends to infinity, you get sigma square. And capital S square is equal to summation x minus x bar the whole square by n minus 1, which is called sample variance, is an unbiased estimator of sigma square. Yes, it is true. Now, if t is equal to 3x1 plus kx2 plus 6x3 by 11 is an unbiased estimator of theta. So this is given. Expectation of t is theta. Then what should be k? 3x1 plus kx2 minus 6x3 by 11 is theta. So you get 1 by 11. 3 times expectation of x1 is 3 theta. K times expectation of x2 is k theta. 6 times expectation of x3 is 6 theta equal to theta. So you get 1 by 11 3 minus 3 theta plus k theta equal to theta. Right? Theta gets cancelled on both sides. So you get theta into minus 3 plus k is equal to 11 theta. So k is equal to 14. Yes, the statement is true. Okay. Now, consistency is an asymptotic property. An asymptotic property is a property which holds good only when n tends to infinity. So, the statement is true. Consistency can be verified under the condition that n goes to infinity. Okay. The sample median follows normal distribution with mean mu and variance pi by 2 sigma square by n. Yes, the statement is true. Remember, x bar follows normal distribution with mean mu and variance sigma square by n, and the sample median follows normal distribution with mean mu and variance pi by 2 sigma square by n. Okay, so the statement is true. Now let us come to the next statement. S square is a consistent estimator of sigma square. Yes, it is true. Remember, the S square is a biased estimator of sigma square, the small s square. But the small s square is a consistent estimator of sigma square. When n tends to infinity, we discussed that it becomes unbiased. Okay. When you don't impose any condition on n, it is biased. But when n becomes indefinitely large, it is unbiased. And it is a consistent estimator of sigma square. If x bar is a consistent estimator of lambda, x bar into 10 minus x bar is a consistent estimator of lambda into 10 minus lambda is true because consistent estimators have a property called invariance property. Okay, this invariance property is possessed by consistent estimators and maximum likelihood estimators. Okay, now the minimum variance unbiased estimator is unique. Yes, it is true. But the unbiased estimators are not unique. Right? They are not unique. Unbiased estimators unique is false. Okay? The consistent estimator is unique. This is also false. You have many consistent estimators and the one which has least variance is called efficient estimator. You have many unbiased estimators and the one which has least variance is called minimum variance unbiased estimator. So these two estimators are not unique. The correlation coefficient between an efficient estimator T1 and any other estimator with efficiency E is square root of E. It is not E square. The statement is false. Okay. This is the correct statement. Efficiency of an estimator cannot exceed 1. It is true because efficiency is computed as variance of T1 by variance of T2. Efficiency of T2 is computed as variance of T1 by variance of T2. Variance of T1 is the variance of the minimum variance unbiased estimator or efficient estimator. So always the numerator is less. So your answer will always be less than or equal to 1. Okay. Now, the Kramer-Rao lower bound is the lower bound for the variance of a consistent estimator? No. It is the lower bound for the variance of an unbiased estimator. Okay, the statement is false. If variance of an estimator is equal to this, then T is MVBE, minimum variance bound estimator. What is this? This is actually the Kramer-Rao lower bound. If the variance of an estimator is equal to the Kramer-Rao lower bound, then T is the minimum variance bound estimator. The statement is true. Okay. Neyman's factorization theorem is used to find sufficient statistic. Yes, it is true. If you are able to express L as a function of t comma theta into a function which is independent of theta, you can say that T contains all information about theta and hence T is a sufficient statistic for theta. T is enough to estimate theta. That's the idea. Okay. Now, next question. If f of x is equal to this, product xi is the sufficient statistic for theta. I am going to apply factorization theorem, Neyman's factorization theorem. Okay. Product of f of xi is L. That is theta x1 power theta minus 1 into theta x2 power theta minus 1 etc. Theta xn power theta minus 1. I get theta power n x power x1 x2 etc. xn. So it is product over xi power theta minus 1, which can be written as theta power n product xi power theta into product xi power minus 1. So this is g of t comma theta and this is h of x1, x2, etc. xn. So this t contains all information about theta. So product xi is a sufficient statistic for theta. The statement is true. Come to this. If f of x is this, product xi is a sufficient statistic for theta. If you know the answer, you can directly say false. If you are not clear, you just compute L, which is the likelihood function f of x1, x2, x2 into f of xn. So 1 by theta e power minus x1 by theta, 1 by theta e power minus x2 by theta, etc. 1 by theta e power minus xn by theta. That is 1 by theta power n e power minus 1 by theta into summation xi. So this is actually g of t comma theta, where t is summation xi into h of x1, x2, etc. xn power 0. So you can say that summation xi is a sufficient statistic for theta. You are not getting any product xi here. It is summation xi. So product xi is a sufficient statistic for theta. The statement is false. Okay. Rao-Blackwell theorem is used to find minimum variance unbiased estimator through sufficient statistic. Yes, it is true. Okay. Now, what is the MLE of theta is x bar if f of x is. Let us verify. I have a doubt here. F of x1 into f of x2, etc. f of xn. So I get theta power n e power minus theta summation xi. Let us find log L, because handling log L is comparatively easy. N log theta minus theta summation xi log e. Okay. Now dou log L by dou theta. I want to find that value of theta which maximizes L. So n by theta minus summation xi. If I substitute dou log L by dou theta equal to 0, I get n by theta equal to summation xi, which implies theta is equal to n divided by summation xi. That is 1 by summation xi by n. That is 1 by x bar. Okay. So theta is 1 by x bar. Now dou square log L by dou theta square, I get minus n by theta square, which is less than 0. So I can say at theta equal to 1 by x bar, L is maximized. So this theta cap equal to 1 by x bar is the MLE. But what is your statement? Your statement says MLE of theta is x bar. So the statement is false. Okay.